Right, well, we've got a Morrison's GU10 LED light bulb which has failed after about 6 months despite the 10-year warranty. You have to keep the receipt, which of course I didn't. So let's take it apart and find out what went wrong. First thing that's interesting to note is that this isn't actually made of metal. It's quite heavy and it looks like metal, but it's actually made of plastic. I found that out when I started trying to get into it with a scalpel. Now, this is going to be quite hard to get apart because I'm fairly sure it's glued together, so I'm going to take it apart and bring you back. Well, that was surprisingly easy to get apart. The lens, the collimator, just clipped in with these 4 clips. So I started digging in around the edge of there with the scalpel and the front just popped off. So we're in, and this has got hot. So for a start you can see some very toasty flux residue around there and the black spot of death right there on that LED. Common failure mode. So we've got one dead LED and this whole fixture is dead. Well, I've got it the rest of the way apart. That circuit board was held in with 2 screws. You can see the holes here where the 2 screws went. Got those two screws out, and then I had to unsolder these 2 wires from here, which was difficult. This is an aluminium PCB. You see, it's aluminium. It's common that as a heat spreader, and getting that hot enough to get those wires unsoldered inside a plastic enclosure like this was quite tricky. Normally the trick is to preheat these before you try and solder them, but obviously that wasn't possible in the plastic enclosure. So I had to rely just on the soldering iron. This thing is a 40-watt iron, but the heater is literally right in the very tip. That little bulge at the end is actually the heater. So it does a pretty good job of heating these. You can see the failure mode in much more detail now we've got it apart. Obviously the actual cause of death was that black spot of death on that LED. But interestingly, I've tested these LEDs and it's not the only dead one. Even though that LED was the actual cause of failure, this thing wasn't long for this world. We can see that for a couple of reasons. The first is the discoloration on this board. You can see where the flux residue around the solder joints has actually got very hot over a long period of time and turned to a brown, crystalline, brittle material. That's an indicative of long-term heat exposure. Now the driver board for this thing, which was right behind it, was mounted in here, like that. So all the heat that has come off the LED, mounted in here, bear in mind this thing's been in a ceiling, so this thing has spent its entire working life like that, with absolutely no airflow around it whatsoever. These heatsink looking fins around the front are just for show, they're only plastic. All of the heat rising off the LED, the very first thing it's done is hit this capacitor. So you've got a capacitor right there, an electrolytic, and electrolytics don't like getting hot. And you can see that this one has leaked. The top has bulged. It's domed on the top. And it has definitely leaked electrolyte. If we look down in here, we can see corrosion. The green is corrosion from the copper wires. And on the edge, that brown residue on the inside edge around there, that liquidy stuff, that's electrolyte from the main capacitor. So, that's how the thing's constructed. In my opinion, it's a bad design. It's got far too hot in just normal use. It's died after 6 months. This thing is supposed to have a 10-year life. If they'd not skimped and made this enclosure of metal, then I don't think it would have failed. I think those fins around the outside would have done their job, and it would have lasted, but they haven't. They've made it of plastic and then painted it to look like metal. Anyway, let's go into this in a bit more detail. Shall we reverse engineer this driver board and see what it does? Right, and here we are with a reverse engineered driver board, which it turned out was actually quite hard to do. They've thrown us way off the scent with the labelling on the board. You can see Q1 is labelled emitter, collector, base, but those labels are incorrect. We'll come back to that in a minute, but that threw me off quite a bit. So we've got a few failed attempts at the reverse engineering before we finally got the correct circuit. So let's look at what we've got here. So at the start of the circuit, we've got a fuse. This thing here is a fusible resistor. So it's a 39 ohm resistor in series with the mains coming in, which if too much current is drawn by the circuit, it'll get hot and it'll break. Next component is this blue disc. This is an MOV. That's over voltage protection. If this voltage here goes above 275 volts, this becomes essentially a short circuit, and that blows this fuse. Then we have a surface mount diode bridge on the back. That's this guy. That's a bridge rectifier, a single component. Inside you've got classic arrangement of 4 diodes. And then we have some smoothing to make some DC. That is these 2 brown capacitors and this green inductor here. That's quite hard to see. It could be red, red, brown or red, red, red. If it's red, red, brown, then that's 220 microhenries, which is a bit more believable than 2,200 for something that size. So I suspect it could well be red, red, brown. And then a second capacitor. So we have reasonably smooth DC at this point now, at about 300 volts. That goes straight to the LEDs. And at the output we have the large capacitor, this brown one, which is a 50 volt 47 microfarad capacitor. We have a diode, which is actually quite a small diode. It's this little signal diode here, wired so that it should never conduct. And then a resistor. This is a 68k resistor, which I believe is a bleed down resistor. That's there so that the LEDs switch off quickly when you turn the power off. It bleeds down this capacitor to 0. That is a standard diode, but it will have a reverse voltage of around 40 volts, and it's there to protect this capacitor in the event that the LEDs are removed. It'll clamp the voltage at this point. Now, because this is an LED driver, it's going to be a constant current power supply. I suspect that these LEDs are multi-chip, because although there are only 6 on there, I suspect the forward voltage of that will be close to 50 volts, which means the current will be very low. It might only be 100 milliamps to get that 5 watts. Now, let's have a look at this circuit in a bit more detail, because it's quite interesting the way it works. We've got 300 volts DC here, and there's no direct path from the negative of the LEDs back to the return. The return is here, and the return is also here. But there is no direct path to the return. It can go through this transformer, but then it hits the switched off transistor. So when this thing very, very first starts, the only current path that can flow from 300 volts back to ground is down here through these 2 1 mega ohm resistors into the base of the transistor, which will switch the transistor on, and then proper current will start to flow. So the transistor switches on with just that little bit of leakage current from here, brings some current through here, which in turn brings current through this transformer. Now, the transformer will couple some of that current across into this side here, which referenced to 0 will force some current through these 280 ohm resistors, through this diode and into the base of the transistor, turning the transistor on even harder. So that's a positive feedback loop that will tend to switch that transistor on. As soon as it starts to switch on, it will continue to switch on. So at that point, what we will have is a ramping current in the LEDs. It will begin to ramp up. But what will be happening as that current ramps up, bear in mind an inductor, if you apply a step voltage to an inductor, you will get a ramping current until the inductor saturates, and then you'll get solid current set by the DC resistance. So that ramping current will mean that we'll have a ramping voltage here determined by these 2 resistors in parallel, 30 ohms, 47 ohms. So as the LED current ramps up, governed by the inductance of the secondary of this, the voltage here will start to increase as well. And at some point that voltage will get high enough that the base is no longer switched on. This 3 volt Zener diode clamps the base at 3 volts. So as this point rises past 2.6 volts, remember there's always 0.6 of a volt between the base and the emitter of a transistor. So as this point rises past 2.4 volts, the transistor will switch off. So that limits the maximum current on the ramp up side, which is 13 milliamps. So what will happen is there'll be, in the time domain, the current in the inductor will ramp up to 13 milliamps, and then it will ramp down. And when it gets below a certain point, the ramp down is it discharging, powering the LEDs while the transistor's off. As it ramps back down below a certain point, this point in the circuit will drop again. There will be a bleed current from here, which will start to turn the transistor back on, and then the cycle repeats. Once the transistor starts turning on, the secondary turns it on the rest of the way, and we end up with an oscillator. And so there'll be a ramping current in the oscillator, in the inductor doing this, with an average somewhere in the middle. Now that's at the 300 volts. This is acting as a buck converter. You can see that the LEDs are actually referenced to the other side of the inductor. What we'll end up with is a trade-off between current and voltage. The voltage across the LEDs will be lower. It'll be somewhere around 50 volts. And the current in the LEDs will be higher. It'll be somewhere around 100 milliamps. And that is fundamentally how this circuit operates. It's a buck converter, so it's pulling less current from the mains to put more current through the LEDs, and it's going from a high voltage to a low voltage. This one happens to be non-isolated. It does have a transformer, but the transformer is really just the basis of the oscillator rather than acting as an actual classic transformer. The secondary on this transformer will be much larger, and the inductance of it is acting really as an inductor in a switch mode power supply, rather than as the secondary winding of a transformer. The primary winding, which drives the base, will probably just be a couple of turns, just enough to drive that base in the circuit up to about 3 volts and hold it there. It's worth noting they really confused me with this transistor. So the transistor itself says 4202BD on it, which you haven't got a lot of chance of seeing, but you can just about see 4202BD, which, if we look it up on the internet, you can see has pin 1, 2 and 3 as the base emitter, collector emitter, which is a dead standard pin out for a TO92. However, if you look at the circuit board, it has got emitter collector base, which is mirrored, as if the transistor was mounted on the other side. And that was really rather confusing. I'll prove it. Look, you can see this point in the circuit in the base, where you've got the 2 different diodes feeding into that point in the circuit, is this pin here, with the 2 different diodes feeding into the circuit. And if we look at the transistor, the way it's mounted, that point there is labelled as the collector. And yet, if we hold this up and look at it like this, you can see it's pin 1, which is the base. And I verified that. I added some resistors to the legs of the transistor and put it into a circuit like this, where I said I did some diode checks, and there is an additional spurious diode in there, which I'm not quite sure what that diode is doing, but my diode checker picks it up, which is a little odd. However, if we were to take the assumption that this were NPN, then the base would be this, which is actually pin 1. I've drawn the package upside down here. And I put it into this test circuit here, wired it up as a transistor switch. Each of these is just 3K9. So I'm not actually expecting any current gain out of it, but it's enough to make it switch, which is all I'm checking in this configuration. I was able to deduce, just based on observing its function using a multimeter, that it was this pinout, which exactly matches what this internet data sheet, which is the best I can find, says about it. In PNP configuration, it appears to work as if we wired it like this with the base in the middle. However, in that configuration, what's really happening this way round is we'd be wiring it as essentially a common base amplifier, which has very low gain but will still switch. So that, I think, is a false positive. Pretty damn sure it's a NPN with the pin out mirrored on the silkscreen on this circuit board. But yeah, that threw me off for a good hour, that did, figuring that through. I'd convinced myself that the circuit worked. If we redraw it like this, this is how the circuit would look if the silkscreen was correct on the circuit board. And these diodes feed into the emitter. And I had this theory that the base was clamped at 0 and that you were putting the emitter, driving the emitter negative to switch the transistor on. But it doesn't actually work, it would just turn on and stay on, as far as I can tell. So that's definitely wrong. And this is definitely correct. The transformer is actually drawn upside down. That transformer should just be that way up to make the whole diagram much more clear. But there it is.